Advanced Higher Physics, Electromagnetism, Electrostatics. Part 2, Electric Fields. Uniform electric fields. A uniform electric field can be produced between two parallel plates with a constant potential difference, that is, a voltage across them. The electric force and the electric field strength are constant at all points in the field. And that's because if we have a look at the uniform field, we have straight lines which are parallel to each other and equidistant from each other as well. So each point within that field, it has the same amount of electric field strength. A force will be felt by a charge within the field, and the size of that force is going to depend on the magnitude of the electric field strength and also the magnitude of the charge within it. Similarly to the weight of an object is equivalent to its mass multiplied by the gravitational field strength. So we say E is equal to F over Q, and we can rearrange that to F is equal to EQ. The force with an electric field is equal to the electric field strength multiplied by the magnitude of the charge, similar to weight is equal to mass times gravity for a gravitational field. Here, force is the electric force in newtons, E is the electric field strength in newtons per kilograms, and Q is the charge in coulombs. The work done on the charge by the field is given by W equals QV, same as what we see in higher. We can also say that work done is equal to FD, which is an equation you were introduced to within National 5. We can equate these two things to each other. So we can say QV is equal to FD. We know F is equal to EQ from the equation above. This then gives us a final relationship of V is equal to ED. Note that W is used for work done to avoid confusion with E, which is also the symbol for electric field strength. Sometimes you will see the E for work done written as EW. But if we use W, it avoids any confusion. Within this equation, E is the electric field strength in newtons per coulomb, V is the potential difference in volts, and D is the separation between the plates, that's the charge plates, with the electric field that exists between them. Potential difference, V. In higher physics, we define potential difference as the energy transferred per coulomb between 2 points, that is W equals QV or V is equal to W over Q. We can now also define it in terms of the electric field and the distance between 2 points by using the information from the previous slide. So in the previous slide, we defined the equation V is equal to ED. Potential difference is the work done in moving a unit positive charge in a uniform field E across a distance D, very similar to the definition we have for gravitational potential. This is similar to how gravitational potential energy and gravitational potential are defined in a uniform gravitational field. We can look at these as equivalents. In a gravitational field, EP is equal to mgh, or V is equal to G multiplied by H. So here's gravitational potential energy and gravitational potential. For an electrostatic equivalent, W is equal to QED, V is equal to ED. Charge in a uniform electric field. If we have a look at a point charge placed within a uniform field, that charge will experience a force. For example, an oil drop of mass 2.00 times 10 to negative 5 kilograms and a charge of negative 6.40 times 10 to the 9 coulombs is injected between two plates 5 centimeters apart. A potential difference of 400 volts is applied across the plates. A. Calculate the electric field strength. B. Calculate the electric force acting on the electron. B. Part 2. State the direction of the electric force. C. By considering the weight of the oil, remember W equals mg, determine the magnitude and direction of the unbalanced force acting on the oil drop. And D. Calculate the initial acceleration of the oil drop. The answers to these questions are on the next slides, but you may want to try them yourself first. Here are the answers. Hopefully they matched up to the ones that you got. If you're unsure, however, let's go through the solutions. So we have our charge placed within a uniform electric field. We're told that the oil drop has a mass of 2 times 10 to the negative 5 kilograms and a charge of negative 6.40 times 10 to the negative 9 coulombs. And we're told it's injected between the two parallel plates 5 centimeters apart. We're going to have to convert that at some point. A potential difference of 400 volts is applied across the plates. And for the first part, we need to calculate the electric field strength. So the electric field strength E is equal to V over D, which is 400 volts divided by a distance, which is 5 centimeters, 0.05 meters, which gives us a value of 8,000 newtons per coulomb. 1 mark for the equation, 1 mark for the substitution, and 1 mark for the final answer. In part B, part 1, we're asked to calculate the electric force acting on the electron. F is equal to EQ, which is equal to 8,000, which we worked out in the previous part, multiplied by the size of the charge, 6.4 times 10 to the negative 9 coulombs, giving us a value of 5.12 times 10 to the negative 5 newtons. We're now asked to say what the direction of the electrical force is going to be. Well, the direction of the force can be determined by having a look at the charge and having a look at the direction of the field. We have a negative charge within the field. It's obviously going to be repelled by the negative plate and attracted to the positive plate, so our direction is going to be up. Now that we have the electric force acting on the electron and we have the direction of the electron, we're asked to, by considering the weight of the oil, determine the magnitude and direction of the unbalanced force acting on the oil drop. Okay, so let's have a look at the weight first. W equals mg. Now we're told the mass of the oil drop within the question, so that is equal to 200 times 10 to the negative 5 kilograms. And we're also told the value of the gravitational field strength. It is contained within the data sheet, the front of the paper. We should know it's 9.8, giving us a value of our weight to be 1.96 times 10 to the negative 4 newtons. Now, we know the electric force is acting up. This is acting down. So the way we show up and down is by having negatives. So our overall unbalanced force is going to be our force going up, which is 5.12 times 10 to the negative 5, plus our force going down, which is negative 1.96 times 10 to the negative 4. And we add those two together, we end up with negative 1.45 times 10 to the negative 4 newtons. It's a force. We should put the direction. The negative direction says this is acting down. We don't really need to put the direction here because we have the negative sign, which is showing us the overall force. Now we're asked to calculate the initial acceleration of the oil drop. Well, this is quite simple. We know that the unbalanced force is equal to negative or 1.45 times 10 to the negative 4 newtons down. So the acceleration is going to be F over m, which is 1.45 times 10 to the negative 4 newtons divided by our mass, which is 2 times 10 to the negative 5, giving us an overall acceleration of 7.25 meters per second, and that is down. because it's in the initial direction. So here's the questions and all the solutions. Now this is a very important example because it leads us on to a very famous experiment called Millikan's oil drop experiment. In Millikan's oil drop experiment, Robert Millikan, who was an American scientist, in 1910, he used charged oil drops to try and deduce the charge on an electron. He sprayed negatively charged oil drops into an electric field. He then adjusted the voltage until the electric force balanced the weight of the oil drop. So he knew what the mass of the oil drop was, obviously knew what gravitational field strength was, and therefore he could say that the weight must be equal to the electric field force. By equating those two things to each other, knowing the size of the potential difference of the field, he could then determine the charge on the electron. So here's a setup, very, very basic. We have oil spray, we have a small gap for one droplet to go through, we've measured the mass of the droplet, we know that the uniform electric field is there, the droplet experiences a force due to the uniform electric field. That force is in the same direction as we had for that previous example, it's in the upwards direction. Weight is acting down, but the oil drop was balanced in between the two. So using a microscope, he determined the volume of the oil using the microscope, and from this determined the mass and the weight of the oil drop. From the electric force, he then calculated the charge on the oil drop. After many thousands of measurements, Millikan finally found that the charge on an oil drop was always a multiple of a basic unit, which is 1.6 times 10 to the negative 19 coulombs. Projectile motion of a charge in a uniform electric field. We know that linear equations of motion can be used to solve problems on charges moving perpendicular, that's at right angles to an electric field. And this is exactly the same as a horizontal projectile moving in Earth's gravitational field, where we follow the parabolic motion because we have the gravitational field causing an acceleration vertically. However, we have a constant horizontal velocity due to Newton's first law. In this case, the force which is causing an acceleration of the particle down the way is due to the electric field. We can ignore gravitational effects here because they're very minimal in comparison to the magnitude of the electric field. We also have a constant horizontal velocity because of Newton's first law. The motion of a charge moving initially perpendicular at right angles to the electric field is parabolic, just like a projectile moving initially horizontally within a gravitational field. The motion of the charge in a magnetic field, however, is circular, and we learned about this in the previous topic when we were looking at particles from space. So here's an example. An electron is fired with a horizontal velocity of 2.7 times 10 to the 7 meters per second into a uniform electric field. The electron is traveling perpendicular field, and we can assume that gravitational effects can be ignored. So here's our diagram. We have a positive and a zero, which means a positive overall. Path of the electron is shown. We're asked to calculate the time taken for the electron to move through the field, calculate the vertical acceleration of the electron, calculate the vertical displacement of the electron at point X, and then when we increase the potential difference to 2.4 kilovolts, state where the electron will leave the field higher, lower, or at the same point as X, and you must justify your answer. So here are the answers. You've got to try and find the solution. Please take note that when we come to part 3 and part A, effectively we're using linear equations from motion in order to do our calculations. The only difference being that we need to find the electrostatic equivalents for calculating force. Have a shot. If you get these answers, that's great. And if we're not, we can have a look at it within our tutorial time. One quick note before we go is the electron volt. The electron volt is a unit of energy. The work done or energy required to move a single electron through a potential difference of 1 volt is equal to W equals QV, 1.6 times 10 to the negative 19 multiplied by 1, and that is 1.6 times 10 to the negative 19 joules. So this is a really useful thing for us to use when we're dealing with energies of charges because the energies are relatively small. It's like, for example, using a light year for a measurement of astronomical distance. The electron volt is a very small unit of energy and is widely used in many areas of physics dealing with charged particles. For example, data coming from the Large Hadron Collider. 1 electron volt, remember as a measurement of energy, is equal to 1.6 times 10 to the negative 19 joules. And so if we want to convert between electron volts to joules, we simply multiply by 1.6 times 10 to negative 19. And this is a useful thing to note because you may see this in some examples.